Hello, everyone. Welcome back to Geology 106. The time is 2:56, so we are going to be starting in about 4 minutes talking about volcanoes, and I am so excited for Volcano Week. You guys, y'all have no idea. I love Volcano Week. So, kind of have a small little outline here in my sketchbook about some of the things that we're going to be chatting about. I did just get the lecture slides posted. Had a busy day. And believe it or not, I actually took the weekend off this time. So things didn't quite get up as quick this week as they normally do. I will post a link, though, to the lecture slides right there in the chat, since I literally just got those posted. So you may not have had time to find them on Canvas yet. So lecture slides there. And how's everybody doing? How was your weekend? How was your Mother's Day? How was your etc.? Go close the door. That way when my husband gets off work, he's like, I don't have to be super quiet. Echo's doing good. That's awesome. All right, still waiting for more people to join. Let's get this a little closer, maybe. I'll probably end up knocking it over if I put it any closer. All right. Oh, also, if you don't have your rock kit on hand, go ahead and grab that now. Yeah. We're going to actually be looking at a few of the samples in your kit, so that'll be pretty awesome. We have a lecture this week that is full of hand samples, demos, right? Things like that. So I love Volcano Week. All right, we had one other person join. So how you doing? One other person. I can tell you I've been having a rough last week. It's been good. Been happy. But man, has it been a lot. My car died. My transmission failed. So dealing with that, you know, working my 2 jobs. And so, yeah, hope you guys don't mind that I actually took the weekend off this time, but had a lot going on there. So got a few more people who joined here. How's everyone doing? Got my tea here too, tea time that I didn't finish from earlier. This is Paris, by the way, from Hardy & Sons, the tea I'm drinking. So good. Hashtag not spons. Hashtag could be spons. But if you're a tea drinker and you have not tried Paris by Hardy & Sons, what are you doing? It's so good. Genesis is doing good. I'm doing good myself. I'm busy. I was just mentioning that my car died. Transmission failed. It's going to be expensive. But I mean, it's still good, you know. Life's still good. Talking about volcanoes this week. It's good. Yeah, it's not my favorite. I'm really sad too because I really like my car. I have a little 2005 RAV4. It's like a little mini Jeep almost. I love it. So we'll see if we can get it fixed. So there's 5 of you here now. If you guys don't have your rock kits on hand, go ahead and run and grab those. We are going to be looking at some of the igneous rocks in your kit. So make sure that you go ahead and grab that. I think I'll just throw that up in the chat because we normally have a few people wander in a few minutes late. Grab your rocket. There we go. All right. So also, for the 6 of you who are now here, the top comment there in the chat is letting you guys know it's the link there to the lecture slides. I literally just got them done. So I know that you may not have found them on Canvas yet, the link there to the lecture slides, but it's there. It's the top comment in case you are looking for that. And again, as a reminder for the lecture slides, if you want to like copy it and make, your own notes on it, I've left a lot of stuff blank so that you can fill in notes as you go. And no, I have not seen The Abyss. But anyways, so you can fill in like notes as you go. If you want to just do it virtually, like in your own Google Drive, you can select File in the top corner there and go down to Make a Copy and then click Entire Presentation. And then you will have your own editable file, since you can't make edits to the one that I've posted, since it's my personal file for that. I'm hoping to try and get more organized so I can get these slides out to you sooner for those who prefer to work with hard copies and prefer to print them out and then write stuff on it. But that didn't happen today. Sorry, guys. Hasn't been happening lately. We'll see if we can fix that. So let's go ahead and get started. Looks like we probably have everyone that we're going to be having for the next few minutes. So let's pull up those lecture slides. We're also going to watch a few videos. Oh no, I forgot my phone in the other room. I will have to go grab that because we're going to watch some videos. Basically, I'm just going to hold my phone up so that you guys can watch other videos, and that's hopefully going to work. All right. I see a lot of you guys there on the PowerPoint. Excellent. Excellent. So again, if you want to fill in notes as you go ahead and click File in the top left corner and then select Make a Copy, Entire Presentation, so that way you can edit it yourself. You get a little bit more organized here with some tabs. Let's see. Could you also link the videos in the chat, says Brendan. Yes, I can do that as well. Well, actually, I don't think I'll need to, as long as you can pull up the PowerPoint, which the link is there, top comment. The links are actually in the PowerPoint. Would it still be helpful, though, to you guys if I post those links in the chat anyways? This is going to be a 1-hour lecture. I'm not sure. We'll see how long the lecture ends up being. Might be an hour. Okay, so posting the links will work. We're only going to watch 3 out of the 4 links just because the top one's quality, doesn't show up very well on my phone and then on this crappy camera that's included on the computer. Thank you, IT. It's just not high enough quality to show the first video. So we won't watch that one. Go ahead and watch it on your own time, though. All right, let's start with that first slide there, though. So this first slide here is the anatomy of a volcano. I intend to also post a photograph that I'm going to take of another diagram that's very similar to this one that I happen to be slightly more partial to, just because you can see a little bit more of the underground part of this, which is definitely more preferable to me to be able to see more of the underground that's going on. Oh, I have the wrong slide up. Hold on. That is not the right PowerPoint. Sorry, guys. So discombobulated and unorganized today. It's because I have so many demos. Also, the lab is coming, just so you know. I have to rework a few things on it. As a result, it'll be posted later today, but I won't have it due at 3 o'clock next week on Monday. It will be due 11:59 p.m. next Monday, just to give you guys a little extra time to work on it, since I don't have it out right this second. And I like to try to give you guys as much of a week as possible to work on that. Okay, sorry guys. So first slide there, taking a look at the anatomy of a volcano. Hopefully you guys have had plenty of time to look over that while I am continuing to get organized. So anatomy of a volcano, this is going to be really important since we're talking about volcanoes this week, and we really need to know the correct and proper terminology for describing volcanoes and all the intricacies of what's happening there. So the, let's see. Oh, Genesis made a comment. Should we try to copy the anatomy of the volcano? Do you mean copying the slide? Because this slide is okay in our notes. If it helps you, I recommend it. I think that drawing and sketching things out really helps with memory and retention. So diagrams that you come across in the book, if you just copy them and re-sketch them out, you will be very surprised with how much that actually helps you retain the knowledge. I'm going to show you guys the diagram though that I have a preference for. I will again photograph this and post a link to it in the Canvas module. Sorry, you guys can see that I painted one of my hands nails and then didn't get to the other one. Story of my life. So hopefully you guys can see that there. It's a little fuzzy. That's okay. It just shows a bit more of the underground cutaway, which I like. This is my lab book from when I took this class as a student at this school, or at least a similar class. That was a long time ago. So anyways, let's go back to that lecture PowerPoint, just chatting a bit more. You can see there that we have the magma chamber. That is the big house, the storehouse for all of the molten material that is below the volcano. And you can see in these striped layers in the block diagram that we're looking at, layers and layers of rock that are solid. Because remember, the crust and the mantle are both solid, right? But we have some areas that are partially melted. We'll go over a bit more about the mechanisms behind partial melting on Wednesday. So the storehouse, though, is in this big giant chamber called the magma chamber, right? And then there is a pipe, is what your book calls it. I prefer to call it a conduit. That's the term that I'm used to. And if you talk to a volcanologist, they would use the term conduit to describe that pipe that goes from the magma chamber to the top of the volcano, right? The main volcanic feeder, the main pipe there, the main conduit. You'll probably hear me use the word conduit from now on, because that's honestly just going to be force of habit, because I'm used to calling it the conduit. The vent. So the term vent isn't, I don't think it's actually labeled on this diagram. The vent is the hole in the top of the volcano. That is the spot where stuff comes out. You can have a vent too that is more of like a fissure eruption, right? Or the volcanic vent. That is just what we call the opening at the top, or the opening from where stuff is coming out of the volcanic vent. Dike. So the term dike in geology refers to a diagonal or horizontal kind of like sheet. It's not always a sheet. Sometimes it's more of like a cylinder that is going away from the magma chamber, right? And it's not necessarily feeding a volcanic vent, but it is like this kind of diagonal this way, or horizontal pocket of magma. So let me take a kind of show you guys on this diagram because it's just such a strong preference here. So this right here is a dike, right? And here we can see sheet dikes, right? This is a ring dike right here. It's kind of in the shape of a ring. That's crazy. Here's another sheet dike, and these are also dikes right here. You can see that this one comes up, and then when they cut out the section, it's actually like a really long sheet. So yeah, all of these vertical and diagonal feeders of magma, that is what we call a dike. And then a sill, the next term in geology, doesn't refer to like a windowsill. It refers to horizontal little bits of magma underground. So let's see. Is it going? I'm getting caught up with the comments. Is there going to be a lecture on Memorial Day, or is it going to be on the following Tuesday? We'll probably do, let me know in the comments, would a lecture on Memorial Day be favorable, or would you guys prefer to do the live lecture on Tuesday? Let me know, for the 5 of you who are actually here. So sill, again, is going to be this horizontal. They tend to follow like the actual rock layers of the crust, because it's like a plane of weakness where that lava can like squeeze its way in there. All right, and then a fissure eruption is where you have a long crack in the ground that opens up and magma comes up from that. We saw fissure eruptions back in 2018 in Hawaii on the Big Island. Who remembers seeing footage 2 years ago of the eruptions in Hawaii? Those were all fissures, just these long cracks that opened up in the ground, actually away from the volcano, the main volcanoes on the island. It was elsewhere on the island that these fissures opened up, these long cracks, and stuff came out. We actually have had in our state's history, we've had massive fissure eruptions. More on that on Wednesday. Honestly, thanks for reminding me, by the way, about Memorial Day. In quarantine, there's like yesterday, today, and tomorrow, and I don't really have many other, that's like the 3 days of the week, and holidays have just slipped past me. I haven't seen anyone in the chat. Let's see. I've seen one from Echo who says, either way is fine, not going anywhere. And chime in, other people, doesn't matter to you, Memorial Day or Tuesday for a lecture. Sorry, my ADD is getting the better of me. I also see Alicia's comment about a pressure relief chamber, kind of. Could you clarify your question for me some more? Let's see. Preference for Tuesday. No preference. Has lecture on Tuesday. Okay. I do like actually trying to have as many people as possible like attend the live lectures, because comment interaction is actually really valuable to me. It really helps me get a read on you guys, and if I'm explaining things as adequately as I can be, because you guys can hop in the chat and be like, hey, is this what you mean? Let's see. I haven't seen a clarification on Alicia's comment, but Alicia, Oh, there it is. Sills and dikes siphon away magma that would otherwise trigger an eruption. I bet that's true. I've never thought of it in those terms. But I don't see why it wouldn't. I mean, that would be the logical conclusion because of how eruptions work and stuff. Yeah, probably. I can't say for certain because I'm not a volcanologist myself. That would be a cool profession. One of the reasons why I love talking about volcanoes is so much is because I had the privilege of taking an entire class on volcanoes. I took volcanology from a very amazing volcanologist, Wendy Borson. So that was awesome. And now I know a lot about volcanoes as a result, but I'm still not a volcanologist. One class does not make you an expert. So anyways, let's go ahead though and keep going with these PowerPoint slides. Next slide, slide number 3 there, shows some more diagrams of what it looks like underneath a volcano. The slide that we were looking at, slide 2, and the diagram I also showed you out of my own lab book, those are more simplified depictions of the anatomy of a volcano and the underground network beneath volcanoes. Believe it or not, yes, those are simplified versions, and they are designed to demonstrate to you the different terms. So they're drawn in a very specific way so that as an introductory level student, you can learn the terminology. However, nature doesn't look like a textbook, does it? Never does. Nature's wonderful. In slide number 3, I have 2 other pictures that are a bit, one of them is an artist's rendering of some volcanic landscapes on the border of the Dominican Republic of the Democratic Republic of Congo, the DRC, and Rwanda. So that artist's drawing there in the top left is out of, I think it was from a National Geographic magazine or something. But I think that's actually a fairly decent depiction of how it is actually a bit more complicated and not as straightforward. What the think of it as like a plumbing system underneath volcanoes and volcanic landscapes. You can still see the dikes and the sills under there, but you can also see how there's not just like one large magma chamber, there's several other ones going on. The picture in the bottom right corner on slide 3 is an actual science. I pulled that one out of, I believe, a scientific paper studying some volcanic landscape in Ethiopia. That might actually be along the East African Rift. I think that might actually be part of that. Not sure. But you can see all those blobs kind of underground that are being depicted in that block, and how it's like really weird and things are in odd places, right? And it's kind of all over the place. And that's actually like a scientific model of what they believe where the molten material is underneath the ground. So you can see it's kind of a messy network. So when you think of volcanoes, it's very easy to think of just the cartoony, like there's a giant magma chamber and then like a conduit going up to the volcanic vent. However, in real life, it is far more complicated than that, usually, because nature's awesome. So slide 4, let's see. I left a lot of the text on there because slide 4 is the outline for what we're going to be covering today. Again, today's lecture is partially why I had you guys like draw out all those key minerals, because they're so important to igneous rocks. The minerals that I had you draw pictures of, the olivine, the quartz, the feldspars, right, hornblende, and the micas, etc. The plagioclase. What else did I have? I show a picture of pyroxene. I think those might be the ones. I don't think I left anything out. So those are going to be really important, focusing on towards the later half of lecture. Anyways, so we're going to be talking about types of eruptions. There are two types of eruptions that we're going to cover. There's quiescent eruptions, and then there are also explosive eruptions. We're also going to be talking about the term viscosity and what that means. We will be talking about volatiles. What are volatiles? Volatiles are the gases that come out of a volcano, whether that's water in a gaseous form, water vapor, right? Or if that is, some type of sulfuric gas, etc. Sulfur dioxides, yeah. So that's what a volatile is. Volatiles are gases that are emitted from a volcano. Some of you guys might remember back in 2018 with those Hawaiian fissure eruptions that there were lots of neighborhoods that weren't safe to go to, not just because of like actual lava being present, but some neighborhoods you just couldn't go to because of the gases in the air. So we're also going to be talking about mineral composition. This is where those key minerals I had you draw at the start of the quarter are going to be kind of talked about. We're going to talk about mafic minerals versus the felsic minerals. We're also going to talk about types of volcanoes because there are different kinds of volcanoes. We primarily break them down into three types: shield volcanoes, cinder cones, and composite volcanoes. Also, you guys will notice that on this slide, there's some color coding going on. There's green text and there's purple text. The reason why is because the green texted items are all related to each other, and the purple text are all related to each other. Notice how quiescent is green, low viscosity is green, mafic is green, shield volcano is green. Got some foreshadowing going on here, etc. And then cinder cone is its kind of own little thing. It kind of does either or, so it's in black text. So let's go ahead then and take a look at the next slide. So types of eruptions. Let's talk about quiescent eruptions. These are also called effusive eruptions. You'll probably hear me switch back and forth between the two terms, quiescent and effusive. There's probably a subtle difference outlined in the wonderful glossary of geology. But I use the terms interchangeably, and for a 101 class, it's certainly acceptable to use the terms interchangeably here for our purposes. And I'll probably switch back and forth between the two, depending on which one first comes to mind. So these effusive, quiescent eruptions, few bullet points to note here. They are what we would refer to as non-explosive. You're going to be like, aren't all volcanoes explosive? Like, it's extruding stuff. So wouldn't that be considered explosive? It's like, I mean, bear with me here. It's not like a bunch of dynamite went off. Whereas the other type of volcano, we have the two depicted there, by the way, the quiescent and the explosive, right? Quiescent are very much more, they're just quieter by comparison. The force of the eruption, as it were, exactly. So one is just far more catastrophic than the other. So a quiescent eruption is not as like, you're not going to have a heart attack when it starts. It's not as like catastrophic, right? So anyways, the next bullet point though that I'll have you guys add in there to your PowerPoints, your notes, is that quiescent eruptions, they produce these fluid outpourings of lava, or sometimes they produce kind of like spatter, right? We'll get to look at that in the video. They might produce kind of like rivers of lava. If you've seen the Earth Revealed videos already, then you've gotten to actually see some depictions of that lava just flowing kind of like a river almost. Sometimes with these quiescent eruptions, you can have some like lava fountaining, right? So third bullet point there that I'll have you guys take notes on for quiescent eruptions, for now anyways, is that the type of magma is different between these two types of eruptions. And when I say the magma is different, what I mean is the mineralogical composition and what is the stuff that is in there. So quiescent effusive volcanoes are often, they're mafic types of molten rock or intermediate molten rock. And that actually controls how the magma, the lava, behaves. And that's why it's actually more fluid kind of outpourings of lava, because that mafic composition, the fact that these rocks are more mafic or intermediate allows it to flow more fluidly. More on that coming soon when we talk about the word viscosity. So let's go ahead and also I should clarify too, for those of you who may need a refresher, when I say mafic, intermediate, and then when I say felsic, what we're talking about, go ahead and grab your rock kits. Yeah, do this with me. So felsic is going to be these guys. This is your granite here, hopefully in your kits. Mine is number 13, but if you have the kit that is cheaper that I asked you guys to get, your granite is number 11. So felsic, right? That means that we have, quartz and potassium feldspar, maybe some micas, and maybe some hornblende. I see it in a lot of granites, right? However, the quiescent eruptions, we're really focusing on that mafic and intermediate. So go ahead and grab your sample of basalt. Where did I put it? Oh, it's over here. So your sample of basalt, that is number 9 in your kits. If you have the larger kit like myself, is number 11. This is, again, made up of like your olivines, your plagioclase, and your pyroxenes, right? That's primarily what this stuff is made out of, those plagioclase and the olivines and some pyroxenes, right? So that's the mafic stuff. And then I regret to inform you that you probably don't have an intermediate rock in your kits. Shame on these rock kit creators. This is like an introductory kit. How did you leave that out? Anyways, if you have the large kit though, your sample number 12 is an intermediate rock. It is that, andesite. The intrusive igneous equivalent to this would be diorite. And again, the intrusive igneous equivalent of this would be Gabbro. My brain is all over the place today. I apologize, guys. My brain is just absolutely everywhere. So an intermediate rock here where we've got some felsic minerals and some mafic minerals in it. I have more andesite here where we've got some felsic stuff and we've got some mafic stuff in there, right? And then, of course, basalt. None of my basalt samples have like visible crystals in them. This is that porphyritic where it's got both in it. This is just aphanitic, where you can't see any visible crystals, at least not through the webcam. So this is your intermediate and your mafic stuff. And once that lava hardens from these effusive volcanic eruptions, this is the stuff that you're going to be left with. It's going to be either basaltic in composition or more andesitic in composition. And again, that controls, it's very important for controlling the eruptive style, what these are made out of. All right, so let's go ahead and talk about, we're on slide 5. We're probably going to go a little over an hour today, guys. So explosive eruptions. Let's go ahead and get some bullet points down there for you guys. These, I like to say that these go out with a bang. So this is as though someone lit a stick of dynamite or a bundle, many bundles of dynamite, and they explode and they go off and they go boom, right? And they're terrifying. You can, be a lot less terrified next to a quiescent effusive eruption than you are near an explosive eruption. In fact, there are people who walk up to quiescent effusive eruptions. You don't do that with an explosive eruption. You don't want to be anywhere near that. No, be as far away as possible, because they go out with a bang. My second kind of bullet point on there is that essentially what happens with these eruptions is that the magma that's inside that volcano, when it erupts, it's blown into teeny tiny bits and fragments. When I say teeny tiny, I mean that's the stuff that becomes ash, right? And so there is magma there. It's just that because it's blown apart in this incredibly, very catastrophic eruption, that magma, rather than flowing out, it just explodes into teeny tiny fragments, and it's just blown all over the place and becomes ash or other smaller types of tephra that we're going to cover, things like pumice, things like ignimbrite. Sometimes you do get, wonder how Mount Rainier is doing. Mount Rainier is a volcano. For those of you guys who don't know, our school system here in Washington is failing all of you because about half my students know that that Rainier is a volcano and the other half don't in my 101 classes, and that's pretty common. Don't feel bad if you didn't know that. Our education system has failed you. And it's not your fault. But yeah, so Mount Rainier, it's a volcano. Mount Baker, it's a volcano. Glacier Peak, volcano. And obviously Mount St. Helens, we know that one's a volcano. Our education system hasn't failed you probably there because it erupted in the 80s when most of your teachers back in primary school and secondary school were alive. So they remember it and they actually teach you that it's a volcano. So the volcanoes though that I mentioned in our state that haven't blown since the 80s, they're quieter. It's not been a lot of activity going on over there. So as geologists, we're not like terrified of them right now. However, that doesn't mean that activity could pick up again in those volcanoes. And that's why it's really important to monitor these volcanoes. And that's also why it's really important to not only monitor these volcanoes, but also build in areas around these volcanoes that are not so much in harm's way. Spoiler alert, we'll talk about this more, but we've already done that. Anybody know people who live in like Buckley, right? Or like Puyallup? Don't buy there. Because if Rainier becomes active again, you are in harm's way if you live there. Anyways, moving on. Explosive eruptions go out with a bang. Magma's blown into tiny little bits and fragments, right? As opposed to lava flows. Sometimes there's lava flows. Otherwise, we wouldn't have, certain rocks that I have in my collection. But not usually. Third point, main point about explosive eruptions is that they are often felsic or intermediate molten rock. So that's when we're talking about things like rhyolite. If it solidifies underground, the intrusive igneous equivalent is your granite, right? So when the magma or lava solidifies from an explosive eruption, it's going to be like rhyolitic in composition. It's going to be ash, right? I have 3 different ashes in this sample here. But what is that stuff made out of? It's usually made out of this felsic stuff. Pumice is also made out of this felsic stuff, right? Moving on. Enough about that. Let's watch some videos. I left my phone in the other room. I'm really sorry, guys. I got to run out to my kitchen and grab my phone. But in the meantime, if you want to watch the first link on that slide, we're not going to watch it together because it just won't show up well on this camera. That first link there is a link to the fissure eruptions in Hawaii back in 2018, for those of you guys who maybe don't quite remember it. But that is a great example of a quiescent effusive eruption. So while I'm grabbing my phone and getting that queued up, go ahead and watch that first link there on slide 6. All right. Hopefully you guys had an opportunity to watch that. I have the third link on that page, though, queued up here. So let's go ahead and watch that one together. You get it going here. It's kind of a long video, so we'll just watch like a little bit of it. And this is a great example of kind of what I mentioned with those effusive eruptions, how they sometimes spatter. The link that you guys hopefully were able to watch just now from the Hawaiian eruptions kind of show that more fluid outpouring of lava. And when you watch the Earth Revealed video, you'll also see these rivers of molten lava. I won't spoil the surprise by watching a video of that now with you guys. But let's go ahead and look at kind of like the more spattering type eruption. It's actually showing up fairly nicely. So you can see the lava there flowing out, right? And you'll see it start to turn a dark black color, right? And that's because it's actually turning into stone. It's cooling off from its liquid form and solidifying, right? And usually the top surface of the liquid rock, the lava, that usually cools off first, so it gets like this little shell on top. So there you can see kind of the spattering going on, right? Here you can see more of that spattering. Anyways, and they form these features called spatter cones. Just kind of keeps building up on top of itself. Anyways, that's enough of that. I'll let you guys watch the whole thing on your own. I do recommend watching more of that on your own, just to kind of get a feel for what that is like. Let me copy the link address for that one. Forgot to do it before I played the video. Sorry, guys. So that is for the one that we just watched. I wish I had a really great example of like the rivers of lava for you guys, but I don't. I'm sorry. I don't want to do that. Sorry. Technical difficulties here. Copy link URL. All right. Here's the link for the next one that we're going to watch. Paste. Enter. And let's get that queued up here on the phone. I happen to love this video. There may be some swearing in the background. I apologize. We're going to be now transitioning into 2 videos looking at explosive eruptions. And after watching these videos, you will understand kind of like the difference between the 2 types of eruptions. So what we just saw previously is going to form stuff like this, right? Or maybe stuff like this. And then what we're going to watch now forms stuff like rhyolite, that lighter felsic stuff, or the pumice, or the, we'll talk more about these terms. I'm sorry, guys, I'm getting ahead of myself. Let's go ahead, though, and watch this video. This is of a volcanic eruption in Papua New Guinea. We're going to watch the whole thing. Here's the volcano. Also, watch the clouds in this video. Did you see the clouds?
Holy smoking Toledo.
Right? I love this video so much that we're going to watch that again. Pay attention when the explosion occurs. Watch the clouds right above the volcano. You will actually see that there is so much energy released when these explosive eruptions occur, that there is a shock wave, and it is, so much energy is released that it will actually push away like the clouds, and you'll see that above the volcano. And that's what hit the people who were far away on a boat, is that there was that bang, that sound, and that shock wave, and you saw the camera shake. And that's because it's like it was probably felt like they got pushed. Just that energy that was released. Let's watch that again. Check out the clouds.
Watch out for the shock that's coming.
All right.
Holy smoking Toledo.
Well, all right, enough of that one. So, and you can hear the guy be like, holy cow, because, it probably hurt their ears. Advertisements. Video will play after ad. Okay. We got the ad to go away. So, That was for chocolate too. They know me too well. They've been doing really well on their marketing there, I guess. All right, so. Oh, hold on. By the time I got it to show you guys, it's kind of already life insurance. Yeah, no kidding. Yeah, I didn't even know clouds could move like that. The only reason that they can move like that is because they literally got pushed around by this volcano. They wouldn't move like that normally in the previous one. So let's look at this other explosive eruption. I'll post the link in just a second.
Open from the side.
What I want you guys to look at is see the various clouds. We'll watch this again. See the stuff there on the side. See this giant plume up above it? We call that the eruption column. Right, let's watch that again. So you guys saw this really large cloud that had formed above the explosive eruption. That's what we call the eruption column. It's this giant column of ash. And volatiles, gases shot up into the atmosphere. You'll also see when we rewatch this, this really puffy cloud that's kind of coming down, puffy cloud coming down the side of the volcanoes. That to me kind of looks like it could be getting into pyroclastic, or excuse me, why am I blanking on the term? Nuaerdant. I'll use that term, Nuaerdant kind of type of territory. That's kind of an archaic term to call it, though. You don't hear too many people actually calling it a Nuaerdant, even though it's okay. So here's the link to this if you want to rewatch it with me on your better computer. And yes, this volcano's name is Anak Krakatau, as Noah pointed out. That means New Krakatoa. Let's get this pulled back up. So eruption column, check that out when we rewatch this. The puffy cloud that's kind of rolling down the side of the volcano, as well as you will see raining out from the eruption column early on in the video. These they almost look like, and we call them this, we call them basically these bombs that are coming out. And I have one, by the way. We're going to be looking at this later in lecture. Or in your lab, you're going to be looking at this. It's very heavy. So picture chunks like this, or the size of a car, or the size of an apartment, raining out of that ash cloud. And you'll actually see them kind of these streamers coming down, right? And that's stuff like this, or like the size of an apartment. Maybe not the size of an apartment. That's kind of, not that it can't move stuff that big. But anyways, moving right along. So watch for those as well. All right, here we go.
Open from the side.
There's that puffy cloud. Hold on for the eruption column. There's the eruption column, part of it. All right, enough of that. You can watch the rest of it on your own. And honestly, that raining sound is probably particles from the volcano actually like raining down. All right, it's hot out. Stay hydrated. Stay hydrated because I have 2 drinks here. Yeah, I'm that kind of person. So let's go ahead and move on to the next slide. Finally, you guys are like, man, you're moving slower than a 7-year itch today. Sorry. Try to get better with my pacing. Let's talk about the term viscosity because that's really important to what is affecting these eruptions that we're looking at. So what does the term viscosity mean? Viscosity means the resistance to flow. So does it want to flow nice and fluidly, or does it not want to flow nice and fluidly? This volcanic bomb right there. Okay. So heavy. My whole table kind of goes like this when I move it. So resistance to flow. Does it want to flow nice and freely, flowing down like a river, or is it just like really stiff and sticky and not really want to flow? So low viscosity, it's in green. What else was in green? The quiescent eruptions. So low viscosity equals little resistance to flow. Think about the 2 L's. Low viscosity, little resistance to flow. It's very easy to get these 2 terms mixed up and confused. Happens all the time. So this would be something to make flashcards for because it's so easy to mix up low viscosity versus high viscosity. Now, which one does that mean? So low viscosity means that it doesn't really resist flowing. So think water in this instance, right? And I actually have a demo for you guys. So water doesn't really have, it has a very low resistance to flowing. It likes to flow nice and freely. Have a demo here for you guys. We'll see how well this works. I didn't try it out before lecture. All right, so I've got my little water container here. I've got my plate, and I don't want to use my water glass. I'm gonna drink that. The beaker here filled with water. Big surprise. The water like flows. Hopefully you guys are able to see that. The water just kind of flows quite freely, right? Across the plate. Low resistance to flow. So the next kind of little sub bullet point on that is what has a low resistance to flow? Minerals that are material that is mafic, material that has a low silica content. So we're thinking, basaltic magmas, or maybe intermediate magmas. So these, it has to be about like, we're talking like 50% silica in here, not a high silica content. And anything that's got about like a 50% silica content is going to be really fluid when it's in its molten state. Also, low viscosity is going to equal a higher temperature, right? So when you're working with magmas and lavas that are of a more mafic composition, right? These basaltic type stuff and intermediate type stuff, they're typically higher temperature as well. So now let's talk about, on the contrast, let's talk about high viscosity. So high viscosity equals high resistance to flow. So think about something like honey as an example, or molasses, right? And guess what I actually have here for you guys? I have honey. I don't have molasses. So you can do this at home. We've got some nice little honey. Got some on a plate here. Mine was kind of crystallized, so I heated it up in the microwave before lecture, and hopefully that decrystallized it enough for the demo. I think so. So if I hold this down here, hopefully we can get this. Yeah, it's flowing. But as you can see, I don't need a container down here because while it's flowing, it has a really high resistance to flow compared to water. Now, I don't want you guys to, when you guys might get a bit confused because I'm really using extremes here in terms of water. Basaltic magma doesn't quite flow exactly like water. It's not that, it doesn't have that low of a viscosity. There is like one ridiculously weird volcano called El Doño Langai somewhere in, I think, Africa, that has really weird magma composition. It's bizarre. And it does actually flow like with the viscosity of water. But these volcanoes that are more like Hawaii, more typical kind of low viscosity volcanoes, more textbook, not outliers. They're going to flow kind of like water, sometimes a bit more like what you actually saw with the honey. And then these high viscosity magmas and lavas, they are going to flow, well, they're really not. They just don't like to flow at all. They're more like my crystallized honey almost, where it just is like, you know, nothing's happening here. It's going nowhere fast. And that's why when these higher viscosity volcanoes or magmas erupt, it just gets torn apart into bits and fragments because the stuff just doesn't want to flow. Whereas when you have these quiescent, effusive eruptions, they'll have this outpouring of lava. So the next slide there is a blank slide, except for two pictures. Two pictures of soda bottle, right? One of them is with the cap off, as I currently have this. It's still sealed. And then the next one, they have removed the cap. They've just removed the cap. Besides just removing the cap, the important difference to notice between these two pictures is that in the first one there's no bubbles and foam on top of the soda. In the second one there are all these little bubbles, right, on top of the soda. No, I'm not from the Midwest, but I still use the term soda for some reason. All right, so now that we've talked about viscosity, let's go ahead and what we're transitioning into here with the soda. So we're going to talk about volatiles. We're going to talk about gases. So if you move on to the slide, the next slide that still has the picture of the opened soda bottle on the bottom, and up on top, there's like this kind of sphere. And that's this just beautiful photograph of this like basaltic lava that's kind of like, it's basically like a balloon. That's what I'm trying to say. What you're looking at there is like a bubble gum like bubble or a balloon. And you're seeing the magma that's starting to solidify and harden into solid material on the exterior of it, but you're seeing like the thin layer underneath is still molten, and there's gas in there that's causing it to expand, right? And you can see it stretching on there. Friggin' love that picture. I was stoked when I found that picture for my lecture slides. Yes. So gases and magmas are called volatiles. So what's really important though to understand is that these gases underground and whatnot, before the eruption, they are dissolved into the magma, soda, magma. And the reason why they are dissolved into the liquid magma is because they're under so much pressure while they're underground there, right? Just like this bottle is under pressure. Some of you guys might not have known that, but these are actually pressurized in order to keep the carbonation dissolved into the soda so that when you drink it, you get that like, I don't know, tingly feeling of the carbonation going down your throat. To me, it just feels like needles. So I don't drink soda or carbonated anything because it's like painful. So basically, they're dissolved into the magma. That's what I want to say prior to the eruption. Then when the eruption happens and you've got like this release of pressure, all heck breaks loose. So the next point down on there, do I want to do my demo or do I want to do the next point? No, let's do the demo. So basically, for an eruption, right? Do I want to do the demo yet? Let me look at my next slide. I'll look at the following slide. No, let's do it now. So basically, during an eruption, what happens is that typically for some reason, either the pressure in here becomes too great. This is like the magma chamber bottle. This is like the conduit here. And the vent is the hole. So either what happens is material is removed from above and that reduces the pressure and then triggers the eruption, or the pressure in here just becomes too great and then that will trigger the eruption. And when I say trigger the eruption, particularly, especially with the explosive eruptions, what happens is that all of the gases that are dissolved in the molten rock start to come out of the rock, and that triggers the explosion. So imagine if I shook this thing and then screwed off the cap, we would have an explosion because all the carbonation would want to come out all at once. So let's go ahead and trigger a baby eruption now. Oh, you didn't really get to see it. Oh no, you can see it now. Some of these bubbles forming here. So that is gas. It's not oxygen. That is gas that was dissolved in the soda because it was under pressure. And I just turned the cap and released some of the pressure in the contents of this bottle. And you know it's under pressure too, because when you twist the cap off of this, the bottle kind of like squishes in, right? Because you released some of the pressure that was inside the bottle. You can't really see the carbonation there now. So you could see the bubbles, like actually the gases that are in the soda dissolving out of it. Let's see. I'm behind on the comments. Let's see. Caramel is also viscous. Yes, indeed. And then also a great Queen song. I'm a fan of Queen, kind of. I'm like a Poser fan. I know a few songs and I'm like, those are great. I actually had Queen playing at my wedding. That was the song I walked out to after the ceremony. And anyways, or they sang the song that we walked out to. Anywho, let's talk about the second kind of main bullet point there on the gases in magma slide. So now we're going to be talking about what are the most common types of dissolved gases in magmas. Water vapor is actually the most common dissolved gas. You'll have like water in the magma, right? And then when pressure gets released, that water turns into a gaseous form, the water vapor, right? And that actually is quite volatile. Water vapor is the most common. We also get a lot of carbon dioxide in there though, sulfur dioxide, And then to a lesser extent, we have some amounts of hydrogen sulfide, carbon monoxide, and helium. Not enough, though, to harvest for our helium shortage. That list is in your book, though, in case you didn't catch all that. So kind of the fourth bullet point there on that slide is that if a volcano releases a significant quantity of this stuff, it can actually alter the global climate. If you guys have extra time, probably don't, but it is quarantine. So if you guys have extra time, Google year without a summer. So there was actually a year in history where basically the world didn't have a summer because one of the volcanoes, I believe it was the volcanic landscape in Iceland, erupted, and the eruption was so large and released so many volatiles into the atmosphere that the atmosphere just didn't really warm up in the summer, the following summer. So it literally was just kind of like winter year round. So year without a summer. Significant quantities can alter global climate. Last kind of bullet point on there for that slide is that the volatile content, the gases that are in the magma, is directly related to the composition of the molten rock. So are we dealing with basaltic molten rock, intermediate molten rock, magma, or are we dealing with rhyolitic molten rock, magma? So it's directly related to its composition. 407. We're going to go late today, guys. We're going to go late today. There's just so much to talk about. You have no idea. All right, so moving on to that next slide there then. Let's take a look at slide 9. That's the number we're on. Oh no, sorry. That's the number that we were just on. Let's move on to slide 10. So now let's talk just a bit more in depth about these quiescent Hawaiian type eruptions for a few slides. So what triggers a quiescent Hawaiian type eruption? What are some of those triggers? It's triggered by the addition of magma to the near surface magma chamber. So volcanologists on like the island of Hawaii are always monitoring like how much magma is in the magma chamber, right? Or in the caldera as well, right? And if a magma chamber gets this influx of more molten material from further down below in the mantle, like even more partial melting takes place for whatever circumstances happened to be the case, and then that molten material finds its way up into the near surface magma chamber. Sometimes you can have multiple magma chambers too. But when it gets into that near surface magma chamber and all of a sudden you have a bunch more material there, some pressure is going to grow and it's going to explode. So let's go ahead. I think that's all I really want to say about that slide. There's a really nice diagram there, though, with a bunch of things labeled on it, right? It's got both eruption styles on there, both volcanoes, right? I'll let you guys take a look at that more later, though. So remember but just remember that diagram shows on the right-hand side, it's showing the more eruptive volcano, and then on the left-hand side, it's showing the more effusive quiescent volcano. But anyways, triggered by the addition of magma to near surface stuff. Let's go ahead and look at slide 11. So quiescent Hawaiian type eruptions. So typically what then happens after you get that addition of more magma into the chamber, there's inflation of that magma chamber, because again, you've just added a ton of material to it. So it inflates, right? And then eventually you're probably going to get some cracks and some fractures at the summit of the volcano, at the volcanic vent. And because when you walk up to a volcano like Mount Rainier, or when you walked up to like Mount St. Helens, well, we're not really talking about quiescent eruptions. Sorry, that's not a great analogy. But when you walk up to a volcano that's not erupting, that's a quiescent like type of eruption, there's not always just like a giant hole that you can look down and see the magma. No, usually it's cooled off and it's sealed over. However, if you get this like a really large scale inflation going on because you've added a ton of material underneath it, you might get some cracks and some fractures at the summit of the volcano. And once you do that, you release a bunch of pressure, overlying pressure, and that allows the kind of soda type reaction to take place, right? And then it allows stuff to actually start outpouring from it. These volcanoes, these quiescent Hawaiian type eruptions, they typically produce fluid basaltic lava. And then just as an extra note on top of that, I also want to say that there's typically, I believe that there's fewer dissolved gases in here, and also just different kinds of dissolved gases in the molten rock. And that makes it so it's not as violent of an eruption. That's a great word, violent. It's not as violent of an eruption as the explosive eruptions. So moving right along, because we're getting short on time, let's talk about explosive eruptions. Changing gears here, and now we're going to be back to the more felsic stuff, the more rhyolitic stuff. Let me pull up something here really quick in my notes. Make sure that your guys' slides are on the same one as mine. All right. I forgot what words I left in for you guys. Oh, we're looking at slide 12 now. Explosive eruptions. So pressure, ... And then what you can fill in there after that ... is that in these explosive eruptions, what happens is that pressure decreases as magma rises up in the conduit. So you've got this magma chamber, right? And if if something happens, the stuff in there, and you've recharged the magma chamber, added more material to it, in other words, or pressure for some other reason has caused stuff to rise up, whatever. As the magma rises and gets closer to the surface of the earth, pressure does decrease. And again, that decrease in pressure is what causes this reaction to take place. So, kind of as a sub-bullet point under that, pressure decreasing as magma rises, dissolved gases form in here, or the dissolved gases form these bubbles, the expanding bubbles, right? And then viscous magma, right, expels. This is the next bullet point on there. Viscous magma expels fragmented lava and also gases, right, from the volcanic vent. So viscous meaning highly resistant to flow. Honey, that's not going anywhere. This viscous magma, right, has all these dissolved gases coming out, and it just blows out this fragmented lava and all of these gases in a very violent way. So it's this reaction, but a heck of a lot more violent. So you end up getting, next bullet point, a rapid ejection of magma. When I say rapid, I mean like you're releasing a ton of material, way more than these effusive volcanoes per unit time. You get this big bang, right? And then all this stuff's coming out of the volcano. So once you then, expel that insane amount of material out of the volcano, what's happened? You've reduced the pressure even more. So what happens if you reduce the pressure even more? That kind of last little bullet point on there under rapid ejection of magma. You cause further expansion and further eruption. That's why these things like St. Helens and whatnot, they just keep going for a while. And they just keep rapidly shooting out material compared to these like effusive eruptions where there's spattering and there's fountaining, right? We're getting a lot of material. But it's not the same as when you have an ash column and pyroclastic flows coming off the volcano. That's just so much more material that's coming out of there, really rapidly reducing the pressure on the conduit and the magma chamber below, allowing that chain reaction to just keep going and continue violently erupting until it's, basically emptied out. So looking at slide 13, talking more about, again, the soda demo that we did. So pressure is exerted by those expanding gases in the magma. So again, we're still talking about that same chain reaction going on here. I'm just going to basically outline it in kind of a bullet point format because the slide, I just talked about it. But I'll just kind of bullet point it for you guys. So pressure exerted by expanding gases in magma exceeds the pressure of the overlying rock. So sometimes what happens is you will get the degassing to occur, and the degassing is enough to blow the top off of the thing. So somehow though, something's got to happen that initiates that degassing, but the degassing itself also increases the pressure. And when I say pressure, what I mean is that it pushes on the surrounding rock when you degas the molten rock. So that then, so the volatile filled magma fractures the overlying rock. It's kind of the second bullet point on there. Volatile filled magma fractures the overlying rock. And then the third bullet point on that slide, magma ascends in the conduit. The pressure drops further as you go up closer to the surface of the earth. And that further creates the release of more volatiles, which push on the rock, right? Push on the conduit, etc. It's just a big old mess. And then that chain reaction just continues up through the conduit, and then you get this big explosion. It happens really fast, right? So chain reaction. All right. Thanks to those of you guys, the 9 of you who are here with me. 4:19. No, we're going longer today than we normally do, but remember, this is a 3-hour class. So normally I lecture for an hour and a half and then reserve an hour and a half for the latter hour and a half for a lab. So I'm actually doing okay on timing here. All right. So let's go ahead and look at the next slide, slide 14. So from slide 14 onward, we're now changing gears from talking about eruptive styles as well as composition and whatnot. And we're going to talk about the last kind of topic for today. Yay. It's still going to take us a little bit though, probably another 20 minutes. Sorry, guys. hopefully only 20 minutes. We're going to talk about the 3 types of volcanoes. We're going to talk about composite volcanoes. We're going to talk about cinder cone volcanoes. And we are going to talk about shield volcanoes and which eruptive style these volcanoes are associated with, and thus which type of molten rock composition they are associated with. So let's start with composite or stratovolcanoes. So this is home. This is home for us. This is Mount Rainier. This is Mount St. Helens. This is the explosive volcano, right? So composite cones, also called stratovolcanoes. I use whichever term comes to mind first, composite or stratovolcano. So kind of the first bullet point on there is going to be that these are mostly located around the Ring of Fire. Coincidence? I think not. It's not coincidence. So these are mostly located around the Ring of Fire. Second bullet point on there is that these are, the way that these things look is that they're typically these very large symmetrical cones. And you can see that in the diagram there posted on that slide. It's just this really large cone and it's very symmetrical. It's not weird shaped or anything. It's just this nice cone that goes straight down. And if you look at Mount Rainier or Mount Baker, you'll see that for the most part, those volcanoes are fairly symmetrical. They might have a few lumps and bumps here and there, but overall, it's still fairly like just kind of a tall cone shape. These volcanoes are built primarily out of layers of cinders and ash, alternating with lava flows. So you do, again, sometimes get lava out of these volcanoes, right? Not as often. You know, this rock and this rock here, especially this rhyolite. That's what I got there. I have more rhyolites that look really crazy, but I don't want to confuse you guys with the colors. Rhyolite can come in a lot of crazy colors. Look up flow-banded rhyolite in your free time. It's kind of cool. Anyways, I don't have you look at it in your lab. Anyways, so you do get kind of alternating layers, right, of this lava flows, that's the word I'm looking for, or other pyroclastic materials that we're going to be dissecting more on Wednesday. Pyroclastic materials like pumice or ignimbrite and, ash, right? Or I'm not sure why they said cinders, because I don't personally, they know more than I do, but personally, you don't really get classic cinders like what we're going to be talking about in there, but they say cinders, whatever. So it's those alternating layers. That's what makes up this cone. So if you were to dig into it, you'd see layers that were once lava, but have now solidified to stone. You'd find another layer of like ash and all this other stuff. So moving on down though to that fourth bullet point. These are usually silica-rich andesites. So we're talking about andesites here, but we're kind of moving a little bit closer to rhyolites. So we're on like this side of the spectrum versus this side of the spectrum. We have, instead of like a 50% silica content, we're now talking about a silica content that's like, let me scroll back to see what it was. Hold on. It was on a different slide. I apologize. Excuse me. Where's the slide that had it? There it is. We're talking about like 70% or greater silica content. And we're also talking about like a lower temperature, right? So usually silica rich and acidic or rhyolitic. Then the second to last bullet point on there, they are associated with those explosive eruptions and having material that we call pyroclastic materials. The last bullet point on there, steep-sided summit, right, that usually goes into these gradually sloping flanks. Okay, let's keep going right along so we can finish soon for you guys. Shield volcanoes is the next type of volcano. Shield volcanoes are really broad structures. They're kind of dome-like, and they're built by the accumulation of basaltic lava flows. So you just get lava flow after lava flow after lava flow of this stuff. Not so much like spattering, but just like what you're looking at with that 2018 eruption of Hawaii, where you saw just immense amounts of lava, basaltic lava pouring out and covering large areas of land, right? These volcanoes, a lot of them are islands, such as Hawaii. They start out a lot of times they start out in the ocean as like seamounts, where you have an underwater volcano. This is the second point on there, by the way. They start out as like seamounts, these submarine volcanoes that eventually continue erupting and having basalt outpour on it, building itself up to an island, right? And when I say broad, I mean incredibly broad. So what you're looking at there, the entire island of Hawaii continues underwater, and it goes out like this, right? Till it reaches like the ocean bottom. That whole thing is a volcano, right? I have a sketch to show you guys here. All right. So I've kind of, well, it's on the next slide. There's a better sketch on the in a few slides, but we'll show it to you guys now. So in my notes here for my preliminary notes here for the lecture, I drew out kind of the different types of volcanoes. This is like, these are not to scale. We'll look at a to scale one in just a couple slides. But here I've got like Mount Rainier. This is the composite volcano, stratovolcano. And this is kind of like what we're thinking about with these shield volcanoes. So it looks like if you were to lay down like a shield, you know, it's just very broad and flat. So, whoops, just tipped over the soda there. Let's go ahead and move on to the next type of volcano. We're going to talk about cinder cones. These are sometimes called scoria cones. I'm not used to using that term though. So let's talk about the way that a cinder cone looks. It's steep-sided, even more so than a composite volcano. If you've ever driven up onto Mount Rainier to go to like the parks or anything like that, or to Mount Baker, the volcano starts quite a ways out, right, and goes up to the summit. Cinder cones are really steep-sided. And cinder cones are different. They're not like a bunch of like fluid basalt flows built up. It's not alternating layers usually of, you know, like, I mean, it is, no, it's not alternating layers of lava flows and then pyroclastic materials and then lava flows and pyroclastic materials. No. It's usually just a loose accumulation of scoria and cinders. What the heck are scorias and cinders, Caitlin? You didn't teach us this term yet. It's okay. Go over it now. So scoria and cinders are like these things here. Let me check and see how that's showing up on the camera. Yeah, that's showing up good. So some of you guys may have seen these used in landscaping. Like my family had a bunch of this in their yard where they didn't want a flower bed or grass. I was growing up. So it's basically a pile of this stuff. And I have climbed on a cinder cone, and it sucks to try and climb up it because you take 2 steps forward, and as you're taking those 2 steps forwards, you literally kind of sink back because you're climbing on a bunch of like loose, unconsolidated things. And as you put a foot up, it sinks back down about half a step. This was very tiring. Just a bunch of loose, unconsolidated cinders and scoria clumps. Third bullet point on there is that this stuff is basaltic in composition. So, basaltic, lots of holes though. So many holes that we get to call it a new term, which is cinder or scoria. Fourth bullet point on there. Some cinder cones do produce basalt flows. However, these usually don't get extruded from the summit. These cones are just made up of such loose, unconsolidated spatters, creating these kind of scoria clumps, right? That the lava can't really go up to the summit of it. It actually just kind of leaks out underneath the side of the cinder cone. And that's what that photograph at the bottom of that slide 16 is depicting, is that there's this lava flow that came out from it. But I wish they'd taken it from the other angle, because you would see that this did not flow off of the side of the volcano. It literally oozed out from underneath the volcano, all of the loose, unconsolidated material. Second to last bullet point, the craters for these types of volcanoes are usually very large, and they're also usually really deep. If you go to, which is it? I think it's like Redmond, Oregon. You can climb up on one of these. Anywho, so craters are relatively deep, and here is the kicker. The last bullet point on there is that they're actually really small. Like 30 to 300 meters small. Like, you can climb up to the top of one. It's going to be tiring, but it'll take you like 10 minutes, maybe less if you're fast. They're not very big. They're like, a few stories tall. They're not like Mount Rainier, where it's a magnificent feat if you're able to summit this, like Mount Rainier. No, these are like a few stories tall. And let's go ahead and go down to slide 17 and take a look at a 2-scale photo of these, a comparison of these 3 types of volcanoes, what they look like. So you'll see that the top one there is the shield volcano. Caldera, they use the term caldera. We'll define caldera, but a caldera, it's the vent. There's some specific stuff, though, that gives it the term caldera. We'll talk about that later, not today. On the lower left there, you see a composite cone, and they actually use the example of Mount Rainier. And then, see, they have a cinder cone there. Even that looks a little big for a cinder cone. So that's Sunset Crater, Arizona. And you can just get a sense for like the different sizes of these things and the different shapes, etc. So let's see where we're at here. Let's hit just a few more slides. Bear with me, guys. I'm going to set you up for doing the lab next. So let's look at some different types of materials. We'll continue more on this when we pick up again on Wednesday, but I really want to get you guys introduced to this so that when I post the lab later tonight, if you want to work on it tomorrow or on Wednesday morning, you don't look at it and go, I don't know what any of this, half of this, the majority of this stuff is. You didn't talk about it yet, Kaylin. So let's go ahead and talk about lava flows for this first slide. And when I say lava flows, I'm specifically on this slide, slide 18, talking about basaltic lava flows. There are two different kind of styles, and it depends on the gases, the amount of gases that are in the lava, because there is a spectrum. Nature exists on a spectrum, right? Of, geology. It doesn't fit into nice 3 categories. It has variation within it. So the first slide pictured there is showing an active flow overriding a Pohoihoi flow. So basalt will usually take 2 different types of morphologies when we're talking about the lava flows. Except in Eastern Washington. Eastern Washington extruded so much copious amounts of basalt. And when I say copious, good grief. I've never actually seen either or Pohoihoi in Eastern Washington. More on that to come, but I think it's because so much magma was extruded then. Hawaii is nothing. So let's talk about and Pohoihoi flows. There is a 4th type called a supervolcano. Yes, and supervolcanoes, though, actually still fit into kind of more, I feel like they're more explosive. But anyways, we're not going to talk about supervolcanoes. If you want to learn about supervolcanoes, though, you can check out Yellowstone. If that one erupts, we're screwed. Talk about a year without a summer? Jeez. Anywho. This is lava, well, it was lava, from a Pohoihoi flow. And it is defined and characterized by this really ropey-like texture, like ropes, right, that are beside one another. And when it flows, it's very interesting. You'll get to see on the Earth Revealed video, this actually like flowing. You get more runny magma underneath it that is warm and nice and hot. And then the top of it, again, this one I believe has less dissolved gases in it. Earth Revealed, correct me. And then that allows it to flow more fluidly, and the top of it will crust over. But this is flowing more fluidly than the flow, right? And as a result of the magma continuing to flow underneath it quite readily, but the top of it crusting over, is you get this like bunching up that occurs as the crusted over material is still kind of warm and malleable, but being dragged along, and it's just bunching up. I definitely recommend going onto YouTube if you want a time sink and Googling Pohoihoi flow. It's kind of like watching fire burn or a river flow. You could just like sit there watching it for quite a while, when you're like chilling out, whatnot. So Pohoihoi flow. Flows, however, aren't flowing quite as readily, comparatively speaking. And these kind of march forward almost like a tank. You'll get to see that in the Earth Revealed video yet again. You definitely have to watch that video. You always have to watch them, but it's so critical for this this lecture, for seeing all the visuals. So this is a piece of why is it called Because when you walk over it, you go, my feet, good grief. It's all pokey and it's, jagged, and this would hurt to walk over compared to this guy, right? This would suck to walk on. And that's how you can remember the difference between the two. So both Pohoihoi and are Hawaiian words. And that's why they kind of have that repetitive name to them. So these kind of like, the lava's a lot stiffer and it kind of like falls off as like it crusts, and then it will like fall off. And then there's more molten material underneath it. check out the video. You'll see more of that in there. All right, enough of that. Let's talk about, instead of basaltic lava flows now, let's talk about pyroclastic materials. So now we're off of like the mafic stuff, and now we're moving on to the more felsic stuff. The felsic, like intermediate to felsic slide. When this molten rock is ejected, we have a lot of stuff happen. So we're talking now about, again, like I said, the intermediate stuff or the rhyolite stuff. So some of this stuff is going to be a little bit more basaltic, actually, that we're going to look at, and some of it is going to be more felsic in nature. But pyroclastic materials, most of these are going to be associated with more rhyolitic stuff. Moving right along. I digress. The first bullet point on there under pyroclastic materials or tephra, I typically refer to it as tephra. So you'll hear me use those terms interchangeably. Tephra is shorter, and so tephra is kind of an easier word. I'm going to start using that today. Particles, definition for you of pyroclastic materials or tephra is particles erupted from volcano. And we're talking particles. We're not talking flows, particles erupted from a volcano, such as, you know, everything that we're about to talk about. So first thing that we're going to talk about, first type, is we're going to talk about welded tuff. What is welded tuff? It is fused hot ash. So we've got ash here. This is Mount St. Helens ash. You're going to be looking at this sample, photographs of this for your lab. So I have different sizes of ash there, right? And then because these ash particles, while still being actually solid, they're not molten, but they're solid, they will still be hot enough. If you get more ash piled up on top of it and you compress it while it's still super hot, it will fuse together. And I have a welded tuff here that I found outside of a dollar store in Ellensburg because some geologist at my university wanted to part with it. And I saw this sucker and I could not leave it. This is the most fantastic example of a welded tuff I've ever seen. So I wish I could actually hand this to you guys. It is heavy. It's ridiculously heavy because it is a lot of ash that was compressed. Ash and other pyroclastic materials that we're about to define that you can see clumps of. But the ground mass here was ash that was compressed and welded together. And this is what it looks like. You guys will have better photographs of this in your lab when I get it posted tonight. I'm going to be working late tonight. All right. Heavy. Let's talk about the next type of pyroclastic material. Let's talk about lapilli and cinders. So these are, lapilli and cinders are small. They're typically being the key word, like the size of a bead or a walnut. I, of course, have a few here that are bigger than that. But like when you climb a cinder cone, you actually have a cinder in your rock kit. It's number 7, scoria. Scoria is really the proper name for the larger sized ones. And then cinder is, I would kind of use that, I think, more for like a smaller bit. Watch me again read the glossary of geology and tell me I'm wrong. So lapilli and cinders, small little guys. That's why it sucks to climb up a cinder cone. Fourth type of material that I'm going to define for you guys are blocks. What the heck are blocks? Block is just, again, a size classification. A block is something that is larger than 64 millimeters. And that is the bottom picture on the side there. So the top picture on the right-hand side there is ash. The next picture down are those cinders. We're skipping that one there, going to the last one, and that is a block. And what you're seeing on that block is a hammer for scale. So that's quite a large thing that was literally projectiled away from a volcano. That's terrifying. Don't want to be anywhere near that. And now let's go to the picture that we skipped over, the second to last one, and we're going to talk about bombs. No, not the kind, not what you're thinking. Volcanic bombs, which is the rock. The incredibly large. These are streamlined because they're ejected as blobs of molten rock. So this is like liquid when it gets ejected out of the volcano. But as it's flying through the air, it becomes streamlined because it's flying through the air as this liquid blob. So much so with such, force that it's being thrown with that it actually like streamlines the shape of it as it solidifies in the air. So this guy hardened like in the air, and I hope you guys can see this. You will want to see this for the lab because you guys have a question about this, and I may have just spoon-fed you the answer. You can see that this is football shaped. It's going to be important. It is football shaped. You may need to look up more information about this though to answer some of the questions on the lab, but getting this 3D view, which I can't give you with photographs on the lab, is very important. So I'm just going to kind of show this guy around. You'll get to see more better pictures though, higher quality of the sides of this thing. I'm not going to hold this one over my laptop. This one's so stupid heavy. So yeah, that is a volcanic bomb. So let's go ahead and move on down to the next slide there. Oh gosh, we're going so much more over time. Thanks guys for sticking with me. You're all such troopers, champs. All right, so scoria. Oh, we're actually going to define the term scoria. Sorry, guys. Cinder, lapilli, again, scoria. So these are larger than cinders. That's what you can write next to that bullet point. And they are vesicular. What the heck is vesicular, Caitlin? Vesicular is a fancy word for holes. Lots of holes. And these holes, as I think I mentioned earlier in the quarter, are created because there are dissolved gases in the molten material, in the lava, and then they pop out of the lava as it's turning into stone. And it's able to leave behind the kind of like bubble that it formed, because it basically, as it dissolves out of the molten material, you literally get a gas bubble that forms and then pops. And this is the remnants of that gas bubble, a bunch of gas bubbles. All right, let's talk about pumice. And then we'll be done for today. Pumice. I have lots of pumice samples. They break quite easily because they're extraordinarily fragile. These are like the felsic. Remember felsic, rhyolated, lots of silica and content. Excuse me. But these are the felsic equivalent of scoria. Mafic, more felsic. Not only that, but this has a lot more dissolved gases. Remember, that's kind of the nature of more felsic lavas, that they have more dissolved gases, right? And this it doesn't look like it, but this one has more holes, right? They're just really tiny. And that's why it's super lightweight, right? Like, it's just so lightweight. You know, it's, anyways, I wish I could hand it to you guys so that you guys could see how lightweight it is. It is so lightweight. This is the demo for your lab because I can't give you guys these samples. Normally in the lab, if this were actually an in-person hybrid or just fully in-person class, I would have you guys actually do this. I would give you guys this stuff. But you're going to need this demo for your lab. Take notes. So up here, I have a cinder in the top sample. What happens if I put it in some water? Let's hear some hypotheses. And let's hear some hypotheses for if I put the pumice in water. What will happen? Sinks to the bottom. Couple more hypotheses, guys. We're almost done. Throw in some more hypotheses. Pumice floats on the surface, gases escape, cinder sinks, pumice floats. Excellent. Thank you guys for your hypotheses. I will spoil the one hypothesis. We won't really see gases escape because these are solid stone at this point. However, they're, anyways, so let's go ahead and see what happens. Scoria sank. If you see any bubbles, yep, there are bubbles indeed. Those are oxygen bubbles though that are kind of caught on the rock. It's not because gases are dissolving out of it. That happens while it's still molten material, and we do not have molten material here. Thank the Lord. That would be a mess to contain. Anyways, here's the pumice. Oh, snap. You guys see it floating there? Oh, there is a good shot of it. You can see the two. So pumice is so lightweight, it floats, etc. There's some more details about why pumice floats and why scoria sinks. I sort of alluded to it. If you guys watch this in retrospect and rewind just a little bit, sort of kind of gave it away a tiny bit. Yeah, I'll let you guys sit with that a little bit more. And if on Wednesday you're still like, I think I have the answer. I think I have most of the answer for this lab question, but I'm not sure. Just ask me and we'll talk about it. So the last slide there talks about volcanic hazards. We'll pick up with that slide though Wednesday because we're going to actually define each of the volcanic hazards. So we'll pick up there and I'll add more slides to the lecture. So thanks so much for sticking with me, everybody. You guys are troopers. You're staying till the end. Let's see, I have a couple of requests that I see for like potentially a live lecture. So, sorry guys, my brain's really all over the place today. Live chat. Thank you, Noah. So if you want a live chat, I see that Noah wants a live chat. If you also want to do live chat, let's see, we have Genesis. So I will also send an invite to Genesis as well. Have a great evening. Have a great evening, everyone else who doesn't want to join the live chat. And yeah, I will see you guys on Wednesday. Let's get that live chat going. I'll leave this up for just a couple more minutes in case additional people want to join in on the live chat. So what you're going to do is for the live chat, I'm going to start a meeting. I'm going to call it Geology 106. Then I will add people. Basically what's going to happen is I'm going to type in your email. I will, Noah, I'm going to use the email I've been using for you. And then Genesis, I'm going to use your student email. So you'll want to log into your student email. Your username and password is the same as it is for Canvas. For your email, you go to google.com and type in your same credentials you would for Canvas, and that gets you into your student Gmail. You're actually given an email from the school hosted through Gmail. All right. Looking up Genesis, looking up your email address. Hold on a sec. Your student email address. Oh, it's such a long email address. Sorry. I don't mean to be impolite. I had a friend in school and she hated that her last name was so long. It was a Polish name and it just went on forever. It went on so long that she actually couldn't fit it all on her SAT when she had to fill in all the bubbles for her name. Okay, so I have sent an invite shortly in your inbox. You will see an email that says, hey, you've been invited to join this this meeting. Click this link, and then it will add you to my meeting. Genesis, ask through YouTube or Gmail. It's okay. So it will pop up. Hi, Noah. So got it. Okay, Genesis has got it. Was there anyone else? Thanks for the lecture. Let me check really quick, guys, to see if there's anyone else who wanted an invite. Nope. Okay. All right. Bye, the rest of you, the 5 of you who are still watching on the live stream. I'm going to end this now. See you Wednesday.